Okay, so I think we'd like to get started if possible, just so that we could give as much time as possible. I think this is a really interesting, very important discussion to kind of end the conference on, and I don't think it's a mistake that Al put us in this room because I think, that this is a very important topic. I'm really excited to have, our colleagues here from MIT share these results. So to begin with, I'll introduce, so we have Tom Reynolds from MIT Lincoln Lab, and we also have Sandeep Badrinath from MIT. He works with Hamza Balakrishnan, if I'm sure a lot of people in this room know her. So without any further ado, we'll kind of let Tom take over and get us started on the impact of EOBT uncertainty on airport surface congestion management.
Okay, thank you, Jeremy. Thanks, everybody, for sticking around till the last presentation. Appreciate it. And so before I launch into the material that discusses the actual analysis of the impact of EOBT uncertainty that we did, I just want to provide a little bit of context as to sort of how we got to this point. So the research team, as Jeremy said, Sandeep, who's a PhD student in the Department of Aeronautics and Astronautics, advised by Professor Hamza Balakrishnan, and MIT Lincoln Lab, so myself, Tom Reynolds, and Emily Joback have been doing this work for the last several years. The work we're going to report on here actually concluded about 1.5 years ago, and so obviously there's been a lot of developments and additional work in this field done since then, but so this is kind of a snapshot of the results as they were then, and just want to acknowledge the support of our sponsor, Chris Dorbian, in the FAA Office of Environment and Energy. And that office of the FAA has been interested in service congestion management for a number of years, particularly as they pertain to environmental benefits. Clearly, the reduction of engines on taxi time has significant benefits to the airlines and the passengers, but it also has significant environmental benefits from fuel burn reduction, which reduces both greenhouse gas emissions, the air quality emissions, and also noise. So we have been developing at MIT service congestion management approaches for the best part of about 15, 20 years. Including some trials that we did at Boston Logan. Some of you may be familiar with the end control studies that we did back in the late 2000s. And that predated the existence of a lot of these surface CDM data elements, such as EOBT. And so we had a lot of interest in how the surface CDM data elements could be used to improve surface congestion management. And that's kind of how we got into the game of assessing how the accuracy of EOBT data specifically related to the benefits you could get from surface congestion management. So that's a little bit of the, as I say, the history of how we got to being involved in this kind of analysis. So I don't need to, I think, tell this audience that we need to try and mitigate service congestion management for the reasons that I talked about, fuel burn, environmental impacts. And clearly the platforms that we've heard about extensively at this workshop, TFDM and ATD-2, the two premier platforms through which service congestion management is occurring in the NAS today. And the effectiveness of these systems, as I alluded to, really depend on the quality of the input data that's going into those algorithms. And from the title of this talk, you can tell that the primary one that we think is really important is the EOBT, or the earliest off block time data. So we were motivated to think about, well, so if I was an airline and I was being encouraged to publish the best EOBT data that I could, that maybe requires me to invest money into algorithms that allow me to predict my flight's EOBTs to a certain level of accuracy, and maybe the amount of money I have to invest depends on how accurate I want those EOBT predictions to be. And so as an airline, I would want to know, well, what return on investment will I get for those those predictive analytics that allow me to publish quality EOBTs. So in a nutshell, that's what that blue banner down the bottom there says. There was a need for analysis to help us figure out what the shape of that curve is relating the EOBT accuracy to the amount of benefits that I would get as an airline, which I could monetize and then calculate my return on investment on. And this also, I think, helps the algorithm designers as well to figure out how good is the data that I'm going to be getting into my algorithm. And so those were kind of the two primary motivations for the analysis that we've done and are presenting the results of here. So just a quick set of cartoons just to baseline everybody. So in a pre-service congestion management world where the aircraft push when they're ready, clearly that can lead to large queues at the departure end of the runways, particularly when a lot of flights want to push back in a short period of time. And so with congestion management, where aircraft are publishing their earliest off-block time, so here in this cartoon we have these 5 aircraft publishing when they're going to be ready to push back. We have some generic congestion management algorithm that's taking all kinds of inputs. That congestion management algorithm is going to vary as a function of the airport, the configuration that that specific airport is in at any given time, how well we know the taxi out times, etc. And that bottom one is obviously the one we're focusing on here, is the earliest off-block time. And then that algorithm can then calculate the target off-block times, or TOBTs, which are then the control point that the ramp controllers are using to determine when to release aircraft. And so then the idea is that then those aircraft can be released in a controlled way onto the airport surface at a time that the airport can actually accommodate them efficiently. And then the excess portion of the queue at the top is being moved back to the gate with engines off, and that's where the benefits are occurring. So this banner here is the same as I had on the first slide. So this is the overall motivation for the work, this need for analysis to assess what the relationship is between the EOBT accuracy and its performance. And these bullets are sort of a roadmap of the different parts of the talk we're going to go through here. So we're going to start off with the development of a modeling system that we developed to allow us to test the effects of different congestion management algorithms, as well as different levels of data uncertainty. So this is kind of the simulation infrastructure that we developed, and the example I'm going to focus on here is Charlotte, but we've done this for a number of other airports. And then specifically talk about how we model the ATD-2 algorithms at Charlotte in this modeling framework. Then we'll talk about how we've, the analysis that we've done on what the empirical accuracy of EOBT data is at a number of airports, Charlotte as well as DFW and Newark. And then finally, we'll get to what Al described as the money slide, which is where we're going to present curves that actually directly relates the benefits you get from the service congestion management as a function of the EOBT accuracy. So I'm going to start off with just a little bit of background on the queuing model, focusing on Charlotte for obvious reasons. And the reason why we want a simulation system like this is so that we can do different variants of the operation at that airport, for example, with and without service congestion management, so that we can directly compare taxi out times and through that calculate things like fuel burn, so that we can do comparisons between different situations. And so what this slide is presenting is just on the left there, it's obviously it's an overview of Charlotte Airport, and it's just kind of highlighting where some of the important queues on the airport surface are. So Charlotte's interesting, as I'm sure you all know, in the terms of its ramp area is particularly complex compared to other airports, such as DFW has a much simpler ramp area. And so therefore we had to put quite a lot of care into modeling the ramp area at Charlotte. So that's represented by a couple of arrival and departure queues in that green box on the right-hand side. And then the other sort of primary queues on the Charlotte service are the departure queues, in this case at 36 center and 36 right, and then the runway crossing queue for the arrivals coming in on 36 left and crossing 36 center. And so this is an example of a queuing network that we developed for Charlotte, in this case obviously in North Flow. We have similar models for the other dominant configurations as well. And then that's the basis of the analysis for Charlotte that we're going to be talking about moving forward. So whenever you develop a simulation system like this, the first thing you want to do is to validate its accuracy. And so these are just a few examples of some of the validation cases that we ran. This is a representative day from June of 2016, and we're just looking at the comparison between the model output for the different queue elements in the previous slide. So we got the ramp queue on the left and the departure queues for 36 center and 36 right that I highlighted. The red is the output from the model. The blue is the empirical data. And you can see to first order, there's a good match. There are obviously cases where the match is less good, and we always have to be cognizant of the fact that a simplified queuing model is never going to be able to capture all of the dynamics of the airport service completely. But then what we really want to do is to get it good enough that it can provide us with realistic comparisons between different situations without being too complex. And so there's often a judgment call in there as to how much time and effort to invest in the simulation system. So that slide was just a single day. As part of the broader validation, we looked at a couple of months worth of data. In this case, these are the aggregate results for May, June of 2016 with Charlotte in a North Flow configuration, which is the case that we had on the airport diagram slide. And so that plot on the left there is just showing the aggregate performance, the aggregate taxi out time predictions over that 2-month period for in the red compared to, again, the model in the blue. And again, there's generally good comparison, but there are definitely instances where there are differences, and we always have to be cognizant of that as we interpret the results. But in terms of the aggregate statistics, so we can break out the taxi time predictions from the gate to the spot, as well as from the spot to the runway, and then the total taxi out time. So we're getting reasonably good performance of the model. I think, again, we could invest more time and improve these numbers, but for the purpose of the analysis that we were doing here, we considered that this was an appropriate level of fidelity. As I mentioned, we also developed similar queuing models for other airports, specifically DFW and Newark, and we will be presenting results from all 3 airports moving forward. So I'll just quickly go through this section, and then we'll maybe take a quick pause to see if there's any questions, either on the phone or not on the phone as in people calling in there, but or in the room here. So now we have this modeling framework. The next thing we want to do is to model the effects of different service congestion management techniques using that simulation system. And so here in this slide, we're just showing a simple timeline for the default case that I talked about right at the start, where we have no congestion management, so people are just pushing back. They push back at the instant they're ready. They taxi out to the departure runway. They maybe have to wait in various points along the airport surface, but there's a period where they have an unimpeded taxi, and then they get into a queue where they wait, and the total taxi out time is just the sum of that unimpeded time and the wait time. So in the world where we have airlines publishing the earliest off-block time, this gives us a clue as to when they're actually going to push back. So in this case, the perfect case where the EOBT is completely perfect and we have a perfect taxi-out time prediction, which the model results I just showed show that we don't actually have perfect taxi-out time prediction. But in this ideal case where we have perfect knowledge of both the EOBT and the taxi-out time, then what can happen is that wait time, instead of being experienced on the airport surface, gets moved back to the gate with engines off. The gate hold time is just identical to the predicted wait time, and then a TOBT, a target off-block time, is calculated by the congestion management algorithm. The aircraft complies with that TOBT perfectly, and by the time they push back and start taxiing, they have an unimpeded taxi to the departure, and they depart with minimal waiting anywhere on the airport surface. So that's the ideal case. In reality, we don't know the EOBT perfectly, and we don't know what the taxi-out time is perfectly either. And so that's where we have to consider the effects of uncertainty, because the main thing we don't want to do is starve the runway of demand. So when there is demand that's being held at the gate, but it can't get to the runway in time, if we lose slots on the departure runway, that's a slot you may not ever recover during the operational day, and that's a waste of capacity. So the buffer that is being used in this diagram is really being used to account for the uncertainty that exists in the EOBT time as well as the taxi-out time. So that buffer parameter, as I say, accounts for that in order to avoid losing runway utilization. And so our highly simplified interpretation of the ATD-2 logic is that the TOBT time is being calculated as a function of the EOBT time plus the maximum of the of 0 and the predicted wait time minus the buffer. So that's basically that buffer parameter is being moved into the gate hold time. And so you can see from this diagram that really the critical parameters that we need to consider in the analysis, and you're going to see the results of moving forward, are these three elements that I've highlighted here in red. So the buffer parameter to account for the uncertainty, how good the EOBT is, and how good the taxi-out time is. So that buffer time is accounting for the uncertainty in those two top parameters. So now we have a simulation framework to model the dynamics of the airport surface at Charlotte, and we have a candidate surface congestion management algorithm. We can now exercise that with real empirical data, and that's what some of these results are showing here is about a 15-day period at Charlotte, just over 6,000 departures. And what we're looking at here is the dynamics of the gate hold time and the taxi-out time reduction as a function of that buffer time that I just introduced. And so what you see is that as the buffer time increases, so that means that there's more and more uncertainty that you're having to account for, the taxi-out time reduction in blue that you're seeing is decreasing. So that's saying as your uncertainty increases, the amount of benefit you're getting from the surface congestion management is decreasing. The line in red is showing the gate hold time. And so what you see that's kind of interesting is that as the buffer time gets very low, you're actually holding the aircraft at the gate longer than the taxi-out time reduction that flight is going to receive. And you're actually, in those instances, starving the runway. You're actually sort of throttling the demand to the runway so much that you're losing departure slots. So the optimal buffer is really the case. It's the lowest buffer time that just gets you the taxi-out time reduction to be equal to the gate hold time. Smaller values of buffer than that, you're unnecessarily holding aircraft at the gate. And these specific results are for a 20-minute planning horizon, different planning horizons will have different optimal buffers. But 20 minutes was the case that we modeled in this analysis to match what we understood at the time they were doing at ATD-2. I'll be interested to know whether those planning horizons have changed since then. But at least that's the general relationship here between the buffer, the gate hold time, and the taxi out time reduction. Okay, so before we get into the empirical analysis of how accurate the EOBTs were that we were observing at Charlotte and the other airports and how that maps the benefits of those airports, I would want to see if there's any questions.
Yeah, I have a couple questions from the app. So the first one, Charlotte has multiple spots. How did you combine them into one ramp queue in your model? Is that the reason why the ramp queue size is different between model and actual data in the two peaks?
So this is why I had Sandeep join me on stage.
Yeah, I can answer this question. So the thing is, for Charlotte, you have different spots, particularly departures. They tend to use 2 spots primarily. So instead, what we are considering for ramp queue is like a virtual ramp queue. An aircraft is said to be in a ramp queue if it has crossed its unimpeded gate to spot time, but it has not yet exited the spot. So this gives us a virtual definition of a queue, which we utilize, and this is sort of the definition of queue which we use to define the ramp queue.
Yep. And to add to that, in my experience, I've been researching the ramp for probably 7 or 8 years, and the ramp is just unpredictable, and to really expect to be able to build a model that can capture all that complexity and the dynamic situation that's happening in the ramp, and on top of that, the controller's decision making, because they're in there manipulating traffic, is quite difficult. And so we don't necessarily expect to be able to model the ramp perfectly. We hope to be able to model the ramp well enough such that it gives us insights into the dynamics on the surface. Okay.
Right. So since we know that there is congestion in the ramp, this was like a first order experiment to capture some sort of variation in the ramp taxi time. Right.
Mm-hmm. And then second question, and then after this we can ask if there's any questions in the audience. But what was the main difference between Charlotte, DFW, and Newark when developing the queuing network models?
Yeah, I can answer you on this one. So the thing is, each of these airports have a different network topology, queuing network topology. For DFW and Newark, we just considered departure runway queues. We didn't actually have a ramp queue. We had a ramp queue only for Charlotte. The main reason was aircrafts had a good delay in the ramp, which was not seen at DFW. So the queuing network topology depends on the delay seen at the airport, and that's how we adapt the queuing models for different airports. Does it answer that?
Yep. Another question here on the app. Did you compare predicted versus actual taxi times by time of day? What was your calibration target? So I think on the slide, the horizontal axis was time of day, but you guys can speak to that probably better than I can.
So we did look at time of day. So in these results here, we're looking at this is obviously again only one representative day, and so clearly we're seeing the different banks at the airport. Yeah, so time of day, and in the aggregate data, we also looked at day of the week. Clearly seasonality effects and things would also come in to more detailed analysis, but yeah, time of day was factored in. Sandeep,
yeah, the other thing is, so what you are showing here is just the validation of queue lengths. You also have similar plots for taxi times, both split from gate to spot as well as spot to runway. And we have a time of day comparison for that. We just didn't show it here, but even those plots show good validation.
Yeah, the slides that will be up on the website will have, in the interest of not having death by PowerPoint last on the final day, I trimmed down the slides a little bit, but the full deck will be, which does have those time of day comparisons for total taxi time.
And then just before we move forward, was there any remaining questions from the audience? And if so, I just would ask if you could please walk up to the microphone to ask so that we have a recording of it. Okay.
Okay. Okay, so the next section is looking at the EOBT uncertainty that we actually observed in the data at these airports. And again, I want to caveat this with the fact that this analysis was done about 1.5 years ago, so it would be interesting to reassess these results with more recent data. And I know, talking to Jeremy, that the strategies that they used in the operational tests of ATD-2 at Charlotte use different variants of the data that we're going to be talking about, so we can expand on that in the Q&A if that's of interest. But so what we're going to be showing here is empirical data for Charlotte. This is for about a 2-month period from the end of 2017 into the middle of February 2018 for Charlotte. This is for a major airline at Charlotte. And so what we did is we took the TFMS EOBT information that we got off the TFMS feed, and we calculated as a function of the look-ahead time what the error in post-process, what the error was of the EOBT at different look-ahead times relative to the AOBT as reported in ASPM. So that, as I understand it, is a brake release signal that ASPM is recording, and I think this is where Jeremy may want to expand on what you did at ATD-2, which was, I think, slightly different than this.
Yeah, so that brings up a great point. And, you know, you have such a simple data element such as actual off-block time or AOBT, and you would think you'd be able to capture that relatively precisely, like when the aircraft starts moving away from the gate. What we found is that the AOBTs that are reported in ACARs, the UI times, OOOI, are not set necessarily by actual aircraft movement. And so there can be quite amount of error just in the actual AOBT times themselves. So for ATD-2, we have, to our knowledge, one of the only data sets of what we think of as accurate AOBTs, where there's a process when the pilot calls the ramp and says that they're ready to push back. The ramp controllers then interact with our ramp traffic console, and that interaction provides us a timestamp that tells us when that pilot was actually ready. And so when you look at this data here, just take it with a grain of salt, knowing that there's uncertainty in those AOBTs that essentially it's hard to mitigate unless you have that data element such as the pilot ready time. And I think throughout this 2-day event, you know, you've probably heard us say this a couple times, that we think this pilot ready time is a very valuable data element that it currently is not in the TFDM requirements.
Okay, so with that caveat, I mean, so what we're defining here as EOBT error could actually be, it's a combination of EOBT error and also potentially AOBT error from the ASPM base data relative to the data that Jeremy just talked about. Ideally, you would be capturing the actual pushback, the actual movement of the aircraft. And so we'd be very interested to explore getting hold of that data set, I think, moving forward so that we can calculate a true EOBT error. But anyway, with that caveat being we're trying to be transparent in so the things that we did here. So then what you're looking at with the curves here is, so every color is a different look-ahead time, and so the red line is 5-minute look-ahead time. So that's basically how good was the EOBT estimate 5 minutes prior to pushback relative to the actual pushback. And then the different colors represent different look-ahead times up to 50 minutes. And so you can see, perhaps not surprisingly, that the distributions get much tighter the nearer to the actual pushback you get. But these curves look different for different airports and potentially for different airlines as well, depending on the algorithms that they're using to calculate the EOBT. And so I just alluded to the fact that we did this for the other airports as well, so DFW and Newark. I'm not going to focus too much on the dynamics here for different reasons, but in general, the same general trend holds, which is that shorter look-ahead times, the EOBT error is significantly lower. And in the next plot, I guess we summarize in an aggregate sense what the standard deviation of those profiles look like for the 3 different airports. And so you see there's, within 20 minutes, there's a pretty stable standard deviation profile. At much longer look-ahead times, we see a breakpoint at least in the data we looked at over these time periods for the different airports. And it would be interesting to discuss why the 20-minute look-ahead time we think is a breakpoint. But I think, as you're planning, what the look-ahead time is for the different congestion management algorithms, you have to factor in how good is this data that you're going to have access to.
So before we move on from EOBTs, we had a question that I just wanted to take advantage of while we're still here. So the question is, are you using only EOBT, or are you including LGTD, or the airline's latest gate time of departure, to increase the data set?
So we were just using whatever the EOBT, the published EOBT parameter was on the TFMS feed. It's our hypothesis that at different look-ahead times, the published EOBT is actually some of these different parameters, whether it's the LGTD or the P time. And I think different airlines maybe use different strategies. And so we didn't explicitly look at those other parameters, but we think that the EOBT field on TFMS is being populated with some of those other parameters when an explicit EOBT is not being calculated. But anything, Sandeep, you want to add to that?
Yeah, that's it, nothing more.
Okay.
We just found something regarding the IGDT time. Do you remember?
The LGTD.
IGDT, the initial gate departure time.
That's different than what they were asking.
Oh, okay, fine. Okay. Sorry. Yeah.
There's a lot of acronyms.
Yes, there are, yeah. Okay. So having got a sense, at least in that time in history, when we have a sense of how accurate the EOBT data was at that time. So what we can now do is combine all the models and the analysis that we've done to now calculate for the different airports what the effect of different levels of uncertainty are moving forward. So clearly the EOBT uncertainty impacts the congestion management. But because it reduces the prediction of the taxi, it reduces the accuracy of the taxi out time prediction, and also affects whether you're conforming to the target push time. And so the bigger the uncertainty in the EOBT, as we've alluded to, the bigger the buffer time you need to add. So this plot at the bottom left here shows the relationship from the different airports of the effect of the optimal buffer time that you need in order to capture that uncertainty as a function of the EOBT error. And then finally on the bottom right, we're now getting very close to the ultimate sort of plot that we're interested in. This is relating the taxi out time reductions. This is really the benefit that you're getting from service congestion management to the uncertainty in the EOBT. So as that uncertainty goes up, you see a decline in the taxi out time reduction, as we alluded to before. And so in these plots, unlike one we showed a few slides ago where we had perfect EOBT information, we're now accounting for both the uncertainty in the taxi out time and the EOBT at the different airports. And the shapes of the curves for the different airports are slightly different because obviously, as Sandeep alluded to, the topologies are different, the congestion levels are different, and so we wouldn't necessarily expect these curves to all be identical, and we see that the shape of the curves does vary for different airports. And so now finally what we're doing here is now the y-axis, instead of being taxi out time reduction, is now fuel burn saving. So ultimately what we want to know is what are the monetized benefits of different levels of EOBT accuracy. And so the taxi out time reductions that we showed on the previous slide, we're now considering the fleet mixes at all of these airports. We know what the fuel burn rates are during taxi for all of the aircraft types that make up that fleet mix at the airports. And we're calculating how much fuel burn is being saved from a given, for a given taxi out time reduction at each of these airports. And so we see the shapes here are slightly different again than the previous plot because the fleet mixes of the different airports are slightly different. And so the translation between taxi out time and fuel burn is slightly different. So here what we've done is we've basically converted the taxi out time savings into an annual fuel burn saving. So we've scaled up the taxi time savings from the previous plot to account for what it would be over an entire year at the different airports. And this is in millions of kilograms, and it's then relatively easy. You take your favorite fuel burn number, whatever that is, $3 per gallon or whatever the right number is for the analysis. We could easily convert this into actual dollars. And in fact, we do have, I'm going to do a shameless plug for, so we do have a journal paper that expands a little bit on this work where we've done the full fuel burn monetization and also present results for different airlines in addition to different airports. But it's at its heart, this is really the concluding plot that shows. So getting back to the question that I asked at the start, which is if I was an airline and I wanted to know how much money to invest in improving my EOBT accuracies, this kind of curve is one that I would go to say, okay, so remember in the empirical data, we were seeing between 4 and 6 minutes standard deviation EOBT uncertainty across these airports. So we're in kind of that middle part of the x-axis there. If I wanted to improve the accuracy by a factor of 2, so instead of having a 4-minute standard deviation, I had a 2-minute standard deviation, and that cost me X million dollars, that would, with curves like this, I can now go in and say, well, how much saving in fuel am I getting for that investment? So I can do a return on investment calculation. Okay, so in summary, I think this audience knows that the automation systems are going to enable significant fuel and emissions reduction. So it's great to see these systems getting rolled out through TFDM across the NAS. The analysis we presented is explicitly allowing us to look at what the relationship is between the benefits that we get from the system and the input data, especially EOBT accuracy. And moving forward, I think it would be instructive to look at how these curves relate to a broader range of airports. In this study, we've only looked at the 3 we've talked about. But also, what does the cost curve look like from an airline perspective? How much money would it cost to reduce my EOBT uncertainty by, say, a factor of 2? Is that, are we talking that there's a 6-month return on investment, or is there a 10-year return on investment for that kind of improvement? And I think these are the kind of questions that we need answers to in order to figure out, what level of EOBT can we expect over the next 10, 15 years. And then it also potentially motivates us to develop more sophisticated algorithms that can either explicitly handle uncertainty in the input as well as other factors that we haven't even thought of yet. So hopefully that's given you a sense of the analysis that we've done and how it can contribute to both future ATD-2 and also TFDM moving forward, and be happy to take any other questions.
Yep. Thank you very much, Tom. So we have a question here. What other actions trigger gate out in ACARs? I think that was in reference to when we talked about the break release. From my understanding, luckily, Isaac, I might call in for a help here, but from my understanding, break release and door closure are two of the main ones. Isaac, if you have any other actions that might trigger that?
Yeah, I believe it varies by airline, and maybe the airlines in the room can speak more to what internal policies are, but I think it's some combination of that, those two, both and or one or things like that.
Yeah, so as we mentioned, that we found out about this early on through ATD-2, where we had, the pleasure of going to Charlotte and looking out the window with timestamps and recording when the actual aircraft started to move, and then correlating that to the ASPM data. And so very high tech, exactly what you'd expect from NASA, I'm sure. So that was the last question that we had online. So we'd now like to open it up to the room. Mike?
Yeah, so the question was, so there's a journal paper being, that's in press, it's been accepted. So we're at the vagaries of the publication schedule of the journal, but I think it's going to be imminent, right, Sandy?
Transportation Science, yeah. It's going to come up in Transportation Science. It's an Informs journal in Transportation Science.
Yeah, it's a TRB journal. So, but as soon as that's published, we'd be happy to share it with anybody who would like to. I do. And as I say, so that gives a slightly more detailed explanation of what we did, and also expanded on the analysis in terms of breaking the data down by anonymized airlines, right, Sandy? We don't identify the airlines, but we and also actually monetizes the results directly, which.
A couple questions. First, how do you decide which runway queue the particular aircraft would go in the schedule? And second question, would you say this is an upper bound in that there is a variability in the unimpeded taxi out time as well? Your pushback times vary, spot handoff times vary, general speeds of taxiing vary. So you're assuming that's all perfect, a single number. So if the focus here is just on EOBT. So just curious about your thoughts.
Take the first one.
How do you decide which runways the departures will?
Yeah, so the first question was, how do we decide which runway aircraft go to in the simulation?
So right now, for each flight, we use the historical departure runway. We don't change the runway assignment. I think that's what even the ATD-2 algorithm does. It doesn't look at load balancing of runways. Right?
Yeah, so in the real operations, the TMC in the tower at Charlotte will select what they call the runway utilization, and it's essentially a strategy of mapping fixes to runways, and that they do load balancing through that to gain efficiency.
Right, so you use historical. That's good.
So yeah, we don't change the runway assignment. We just take the historical runway assignments for that flight. Yeah, and
the second question was, given the uncertainty in other processes on the surface, such as pushback or taxi time or whatever, do you consider these benefits to be an upper bound, a lower bound, right in the middle?
So the thing is, we quantify the error in taxi out time. So the actual taxi out time is coming from the data, which has all these uncertainties. And our model has the some constant unimpeded time depending on the gate runway pair and a wait time determined by our Q model. So the difference between these two quantifies the error, means quantifies the uncertainties, and the sort of buffer that we pick depends on that uncertainty. So I can't exactly tell whether it's a lower bound or upper bound, but it is sort of representative. Yeah, I can just say it. The EOBT variability is coming from the data. So from the data, we try to empirically determine what is the sort of EOBT uncertainty for different look-ahead time. And then while presenting these results, we carry out a parametric analysis by varying different standard deviations of the EOBT error, and we run the simulation to get the benefits. So it is a sort of parametric analysis for different EOBT uncertainties.
And I can maybe provide just a little insight, which is all these uncertainties, like, such as in the pushback process or taxi process or whatever, should manifest themselves in the service rates that you see at the spot or at the runways or whatever. Not so much maybe at the runway because you have pressure on the queue and it should be kind of flowing consistently, but definitely in the run or in the ramp area, you can imagine that as those uncertainties in your trajectories builds, those service rates of how aircraft are actually crossing the spot should look different. And I think that, he's being informed by the actual data to learn about those service rates, and those service rates are then what's driving his Q model.
Right, yeah. Yeah, the other important thing to note is that we pick the buffer size based on the EOBT uncertainty to make sure that there's no delays. In a sense, there's no throughput change at the airport. So that is something important. No, it's going to be based on EOBT uncertainty as well as runway separation time uncertainty. So it's taxi out time.
I did not see that in the model. That was my point. It needs to be both.
Yeah.
So
And you're doing that. That's good.
So in the perfect EOBT case, we consider taxi out time uncertainty coming from the runway separation times. But when we look at the buffer with more EOBT uncertainty, we look at taxi out time uncertainty plus the EOBT uncertainty.
Got it.
So they do that analysis where Tom showed, where they look at the taxi time savings versus the gate hold. And when those things are on top of each other, that kind of represents that there's pressure maintained on the runway and that you're not losing efficiency at the runway. Yeah. However, once you have more gate hold than taxi time reduction, then you're starting to potentially dry the runway out.
Yeah, I understand that one. Thanks.
Any other questions in the audience? Okay. So yeah, thank you guys very much for coming, and I think these are really exciting results when you consider that last slide, that Tom showed, and then you consider what he kind of laid out there, which is that when you think about this trade-off between EOBT uncertainty and the benefits, are you talking about 1 year? Are you talking about 5 years? Are you talking about 10 years? Because that makes a big difference, right? And that if you make a good EOBT model and you get to accrue those benefits over 10 years, that's a lot bigger savings than just making a good EOBT model and accruing the benefits over 1 year. And one thing that I would just leave everybody with is that we're showing one piece of the pie here with EOBT benefits. EOBTs are used throughout the NAS in many different functions, and you see some benefits here with surface metering, and it looks great. You're getting other benefits potentially with good EOBTs with overhead stream insertion and other kind of TMIs throughout the NAS. So this is a piece of the puzzle here, and that overall there's other kind of motivations that really drive the benefits once you get those EOBTs good. So I think this is really exciting work, and really fortunate that we're able to kind of be a part of it and collaborate with Tom and Sandeep. So thank you everybody for coming.